Trigonometry, Chapter 1, Trigonometric Functions, Section 4, Using Definitions of Trig Functions, Video 11, Using Identities to Find Trig Function Values. This series is based on content from Pearson's Trigonometry, 12th edition, by Lial, Hornsby, Schneider, and Daniels. And this is the last video for Chapter 1, Section 4, and the last video for Chapter 1. In the previous video, we discussed the quotient identities. You need to memorize these. I know I sound like a broken record. Frankly, I'd memorized the top one and reciprocated to get the second one. And before that, we discussed the Pythagorean identities. You need to memorize these too, and all the algebraic versions of them where you move things around. And before that, we discussed the reciprocal identities, and you need to memorize these too. I kid you not. You need to memorize all of these. Now, in my classes, I don't require them to memorize every identity we will ever encounter because there are many, many more in the future. But I always require them to memorize these because I know how critical they are in not only trigonometry, but in pre-calculus and any calculus course that you take, save business calculus, which is not trig, doesn't include trig. Now, there are several places where using identities makes a problem easier, or in some cases, just flat out makes a problem solvable. In this video, we will use these identities to find values of trig functions. For example, given that cosine of theta is equal to negative square root of 3 over 4, and sine of theta is greater than 0, find sine of theta and tangent of theta. Let's see. Well, maybe we should find a quadrant first. We played that game before. First, from the fact that cosine of theta is less than 0 because it was given to us as a negative, and sine of theta is greater than 0, we deduce that theta is in quadrant 2. When cosine is negative, that means quadrants 2 or 3. Sine is positive in 1 and 2. The overlap is quadrant 2. We may or may not need this information, but at least we have it now. Now, since we know the value of cosine and want to find the value of sine, we look for an identity that involves both. Do you know which identity it is? This is how you play the identity game. The identity that involves both sine and cosine is the Pythagorean identity. I prefer sine squared plus cosine squared equals 1, even though in the previous video, the cosine was written first. That was just a consequence of how we approach the proof. So we're going to use this trig identity, and we're going to substitute what we know. That cosine of theta is negative square root of 3 over 4, being squared because of the cosine squared. If we square that fraction, it becomes positive. The square root of 3 becomes a 3, and the 4 becomes a 16. So we have sine squared of theta plus 3 over 16 equals 1. If we subtract 3/16 from both sides, 1 is the same as 16/16 minus 3/16 is 13/16. Take the square root of both sides, cancel the square, use the plus minus, and on the right side, the square root of 13 will stay the same, but the square root of 16 on the bottom becomes 4. However, we were told sine of theta was greater than 0. So for this problem, sine of theta is equal to the square root of 13 over 4. Also because theta was in quadrant 2, which we deduced earlier. Now that we know cosine of theta equals negative square root of 3 over 4, and sine of theta equals square root of 13 over 4, how can we find tangent? Which identity can we use? I needed an identity that involves tangent and cosine and or sine. Aha! Quotient identity. Sine of theta over cosine of theta equals tangent theta is precisely what we need. Tangent of theta is sine of theta over cosine of theta. We know the values of both. Substituted. We're dividing two fractions, so we multiply by the reciprocal of the second one. And we get the square root of 13 over 4 times negative 4 over the square root of 3. The 4's cancel, and we have a negative fraction that looks like this. But we could rationalize the denominator by multiplying both sides by the square root of 3. The bottom would become just 3, but the top would become the square root of 39. And that's where we would stop in terms of finding tangent of theta. Now, it's worth mentioning that we could have also solved this like we did in a previous video using quadrants and the equation x squared plus y squared equals r squared. So it's an alternative approach that's more algebraic than geometric. Also, it's worth mentioning that we could get all 6 trig functions values by taking what we currently know cosine theta, sine theta, and tangent theta, and using reciprocal identities? If you did, here's the values you would get. I encourage you to go back and try to calculate secant theta, cosecant theta, and cotangent theta and verify that these are their values. Now you try. Pause the video and try the following. Given that sine theta equals the square root of 2 over 6 and cosine theta is less than 0, find the values of the remaining trig functions, tangent, cotangent, cosecant, and secant. All right, here's your fair warning if you haven't paused the video yet. Solutions in 3, 2, 1.